Hi, and welcome to this quick look at an organic synthesis multi-step typical exam question. It's aimed at second year students as opposed to first year students. So we'll go through each section in turn. It starts off by saying if a student plans a two-stage synthesis of alanine from lactic acid. It obviously gives you the structure of both of them. And the main thing to consider when doing this type of question, which is very popular and very common with lots of exam boards, is look for the functional group changes and deal with one at a time. So looking at it closely, you can see that only one side of the molecule is actually changing. So you've got a carboxylic acid functional group there, and in alanine it's still in place. So you don't have to worry about that. It's only getting primary alcohol to a primary amine. Now remember, the student is planning a two-stage synthesis. It says that up here. So don't try to do this all in one step. It's tempting. If you have ideas about how to do it in one step, don't try to make that happen, because what they want you to do is think about it in two steps. So the normal way to go is by a haloalkane. So you need to take solid sodium bromide, or you could do sodium chloride or sodium iodide, doesn't really matter, and you reflux this with concentrated H2SO4 to produce the bromide ions in situ. In other words, they're made in place. They're not sort of obtained from a bottle on a shelf somewhere. They're made in situ because they'd be formed as HBr, which is quite dangerous to store. So you produce a good quantity of bromide ions, and they nucleophilically substitute the OH. So they act as a nucleophile. So the intermediate compound is the same as lactic acid, apart from the fact that the OH is replaced by a Br. Now, like I said, that could equally be Cl or another halogen like iodine. And to get from there to alanine, you use excess NH3, which is another nucleophile that replaces the Br atom, and an ethanol solvent. The ethanol solvent is there to stop the water that's present in the aqueous element of the reagent to actually behave as a nucleophile itself. So you can see from the mark scheme the kind of things that we're allowed to do. So the next part of the question is about organic compounds containing nitrogen, and it's mentioned sodium cyanide can be reacted with many organic compounds to increase the length of the carbon chain. So the cyanide ion is an organic chemistry tool. It basically builds another carbon onto the chain. But to do that, you've got to give it something to substitute with. So it's going to be a nucleophilic substitution, like we said. And it tells you what you react your 1-chloropropane with, and it's ethanolic sodium cyanide. So again, we don't want water present, because water could interfere as a nucleophile itself. So you start off with your 1-chloropropane, and you put your dipoles in, because you can see they're telling you to put dipoles and curly arrows. So you put your curly arrows in, properly placed like that, and that gives us this product. So you can see I've taken the chlorine atom off and replaced it with C, triple bond N, and that gives you Cl-. So looking at what we just constructed and checking against the mark scheme, you can see it's a similar kind of setup, so we get the marks there. Okay, moving on. So here you've got a typical multi-step organic synthesis layout with missing reagents and an unknown compound that you're supposed to deduce the structure of. So starting with reaction number 1, you've got sodium cyanide in acidic conditions, and you can see the CN group added on. So this is a nucleophilic addition because there's no side product. You can see that in the box. So remembering that when you add the CN group, you actually add one carbon atom to the chain. So working backwards from the fact we've got 2, you must have 1 in the starting compound. So if you recall your nucleophilic addition, you'll know that carbonyl compounds such as aldehydes and ketones are susceptible to this type of reaction, so it must be methanal that we're starting from. You can't get methanone because the structure of a ketone would require at least 2 carbons, one each side of the C double bond O, so it has to be an aldehyde we're using this time round. So in this reaction, the next one I'm going to do is number 3. So the functional group changes from the nitrile to a carboxylic acid, which involves hydrolysis under acidic conditions. It's always a good thing to name the acid you're using, so I'm going to go for HCl. You could just as easily use something like H2SO4. So finally, it's reaction number 2 I'm going to look at. And here you've got a nitrile turning into an amine. So this is being reduced this time round. Note the addition of hydrogen always means a reduction. So checking our mark scheme, we can see we would have picked up the marks for each of those changes we've made. Okay, as always, thanks for listening. Until next time, see you soon.